when the temperature go down from 300K go down to 90K, you see the bond distance this little bit shift to the shorter bond distance. However, for nickel titanium, they moved away. But from the future about the intensity in here, basically the temperature go down to low temperature, you will decrease it because the temperature, the deviable factor basically will strong influence your future about the intensity. So when you go down the temperature to the 90K, it's very low temperature, you will enhance your intensity. But if you compare to AB prime here, the first peak, you don't significantly reduce your intensity. Even temperature go down to the 300K. That means if you consider the future in here relate to deviable factor basically conclude the two terms. One is thermal term, one is the static term. Okay? So if you low temperature to the 90K, supposedly you will enhance your future significantly because your thermal term become very small because temperature go very low temperatures. But from the nickel Ka axis, we didn't see significant reduce the intensity. That means your thermal doesn't play any loads in low temperature, but your static look like you become the very important or enhance your structures. Okay, so this is quite interesting. Why the temperature go down from 300 to 90 degree K, your feature didn't show any significant enhance. Okay, because supposedly in our experience, your temperature go down to 90 K, you will have very strong enhance your feature because your thermal term becomes smaller. But in this case, doesn't show this. Okay, so it looks like the nickel structure in AB plane, like we call this phono softening. That means your structure seems breaking. Static become play the major role in here, and the temperature seems like doesn't play any significant role to reduce your future in here. So also we measure the moment KH. This is another thin line, okay? But this thin line we can go down to 9K and 6.5K, okay? Can go down below the spin glass temperatures. You look at this here. Usually you go down to low temperature, you will enhance the future in here, okay? But you also see the manganese KH. The first peak is manganese oxygen. Second peak, manganese or nickel bond distance. CX, you also can see all this, okay? So right now we try to solve or we try to explain why the system manganese nickel titanium oxide is proposed like an XY spin glass or torpedo system, rather three-dimensional Heisenberg's structure. Okay, so we from the neutron we can approach temperature 1.5A and 12K. We can obtain the correlation length. All these corresponded to 72. If you look at this, AB plane usually is much higher correlation length compared to CX. Okay, so it looks like AB plane play the major role in this vortex system. However, if you compare the two manganese, either nickel-nickel or nickel-manganese, the bond distance, okay, if you consider correlation function, if you put the number 3 different kind of temperature, you can get all this number. Also, you have the excess information to get the distance between both two manganese ions. You can calculate the correlation function between AB plane and the CX ratio, okay? So AB plane, the correlation function usually have the higher numbers compared to the CX. That means they can become the most strongest correlation on the AB plane rather to CX. But this number seems not quite significant difference. Okay, if you compare the correlation length rather correlation function. Okay, so AB plane correlation length quite large, that understand. Okay, but the correlation function seems the ratio between both AB plane and CX doesn't change too much. I just mentioned that we can solve some kind of spin property. Also, we see the lattice, some of the interesting point. But how about the charge on the orbital about this system? I just mentioned we also carry out some of the risk measurement at the NSRC. This bin line initially by the Professor Huang Dijin. He also is the deputy of NSRC. We have carried out risk in this bin line 5. As I mentioned earlier, risk basically provide the information about the DD excitation or charge transfer. Neutron, if you have very high resolution, you can get this information. But so far, it's not easy. Use the risk get the information about this kind of physics. So we select. We can run the X-ray absorption. We can instant 3 different types of energy to see the risk measurement. If you look at this, I believe people in this audience just compared. We use the C3 instant photon energy. If you see when the 300K, the AD and the C plane, you don't see too much difference, okay, in this feature. But when the temperature goes down to 30K, that's mean very close to the transition temperature. You will see the AD plane and the C. It looks like the different kind of features come out. This feature basically involves the charge transfer. Okay, so when this sample go down to the transition temperature, it looks like they had some kind of charge transfer effect occurs this system, particularly for the CX. Okay, so the CX, if you look at this feature, okay, you can reference some kind of sample nickel oxide. You can see so many different kind of feature here. How can we explain this feature? Okay, there is some kind of Sugano's Tanabe diagram. Okay, if you get familiar with this kind of group theories, you can plot this correspondent which peak correspondent which state. Okay, I just mentioned why you see the charge transfer occurs when temperature go down to 30K, particularly for the CX rather to AB plane. Okay, so you look at this. I just mentioned nickel, because your bond distance doesn't change even you go down to low temperature. Okay, but the CX, when the temperature go down to 90K, the CX bond distance becomes smaller. Nickel and oxygen, the bond distance becomes smaller. So it will help you to the charge transfer. Okay, so we use the local atomic structure, which can also to help to explain this why you see the significant charge transfer in the interlayer plane rather to AB plane. We also carry out the manganese. Okay, but manganese doesn't significant difference based on our risk measurement here. Okay, so it looks like the nickel plays a much important role compared to the manganese in this system based on our measurement. We also measure the Lennox. Lennox basically provide the electronic structure. If you're familiar with these techniques, not only this, we also can carry out XLD. XLD generally give you the information about the orbital preferring. Okay, you also can see that when the temperature go down to low K, I mean the 7K below to transition temperature, both two show different kind of positive or negative the future here, which implied the temperature go down to below the spring glass temperature. The nickel orbital, 3D orbital, look like change to the 3 0 square minus r square rather to s square minus y square. Okay, so the orbital, the preferred, it look like the change compared to the manganese. Manganese doesn't see too much difference. Okay, so we get this kind of information. We try to understand whether this sample have the orbital ordering or not. Okay, this just gives you the orbital preferred. Okay, that's mean the majority feature is like orbital is like x square minus y square, but low temperature like prefers the z square minus r square. Okay, based on these techniques. So we try to understand whether this also have some kind of we call the orbital ordering or not. So we also carry out so accurate scattering. Okay, so accurate scattering, they just give you, if you have very ordering orbital, you change from orbital ordering to non-orbital ordering, your diffraction peak will significantly reduce with the temperature. Okay, that's generally the technique we use. Okay, so we can measure this so accurate scattering use nickel, because manganese we don't see too much significant difference. However, the nickel we see the quite interesting the difference compared to high temperature and low temperature in terms of the orbital preferred. So we try to understand the orbital ordering whether also occurs this system or not. Unfortunately, we carry the temperature 8.5 K, that's below the spring glass temperature. If you can see the orbital ordering, you will see very strong so accurate scattering peak. Okay, but we below we also scan angle, very widely angle. We didn't see any significant scattering peak. So we will try again, try to make sure that all the measurement is correct, because we didn't find any orbital ordering for these particular systems. This measurement actually are associating KH from the H here, which tell you the valence state. Okay, if you familiar with these techniques. So we compare the nickel oxide and the three different kinds of temperature. The H seems a current significant shift or move, either left hand side or right hand side. This implies the nickel valence state in this system is close to the 2+ valence state. Okay, the H doesn't significant difference. The manganese, we also see similar the measurement. The manganese also the 2+. Okay, doesn't see too significant difference. So I just try to present some of the measurement, but this just very preliminary. We still have a lot of work to do, even include because end of this month we will run the small angle neutron scattering. Try to get the more direct information about the vortex structure on the AB plane rather CMS to support strongly about our study. If we can carry out neutron small angle scattering, that's mapping the vortex state. However, based on our preliminary result, we do see the when the temperature near spring glass temperature, we do see the bond distance for nickel. It seems like it kind of small, but the orbital more preferred AB x squared minus y squared. But the manganese, we do not see too much change, but the bond distance seems some kind of variation. But we also see the XY spin glass states. That's indirect evidence based from our coherent length, how big or how small compared to the AB plane and the CX. Okay, but from X-axis we can see the very strong lattice distortion on the AB plane rather CX. It looks like they have some kind of phonon softening. We still need to more carefully to study these systems. So we try to correlate all these physics parameters together to give some kind of interesting picture to explain this system, whether this system really like Toledo structure. Also, this spin property involved or react to charge, orbital, or lattice or not. Finally, I think I still have 5 to 10 minutes. I'd like to introduce somehow our TKU, Tamkang University, N station, which construct an NSRC. I think people already know the NSRC also construct the new Taiwan photon source at Hsinchu. The first state, they built 7 B9 in TPX in phase 1. Fortunately, our group also had shared one synchrotron source in TPS. Basically, this budget provided by the NSRC also the most strongly. We have the one synchrotron source. The energy covered to 280 to 1500, which covered from the carbon to aluminum, all the elements we can carry out the measurement. We can also have very high energy resolution. This B9 include 2 institutes to show this facility. One is Mass-Fun Institute, one is our Tamkang University. These systems include 3 parts. Okay, one is VLS. This generally can measure X-ray absorption, X-ray emission, also risk. Okay, all kinds of synchrotron techniques involved to probe the electronic structures. This facility can carry out. Not only we can carry out to measure the electronic structure, we also can do some kind of photon or luminescence, photoluminescence study. XEOL we call the X-ray exciting optical luminescence. Usually we measure the luminescence use the laser, but the laser only select very specific low energy. Okay. In this system, we can use the synchrotron to pump your electron. Okay. Particularly, the synchrotron can carry out the very wide energy range. Okay. Also, the energy, also atomic selected the photon energy. Okay. We also can carry out the X-ray MCD, which measures the X-ray magnetic circuit dichotomy. So we can study magnetic material to solve the spin moment and orbital moment. Not only this, we also have the system. We can do the liquid, also gas systems, rather solid system in here. We propose in the future, supposed to end of this year, we can start to commission this facility. We can do the transition metal oxide or highly correlated electronic system. We can study all these interesting physics. Also, we can carry out the energy materials, particularly battery catalysts or some other most interesting the material involved the energy. Okay. So finally, I'd like to thank the people from our groups, particularly people from the NSRC, Li Hongji, Cai Hangmin, also Professor Qiu Zhaowen from the Kaohsiung Daxue, also some of the staff from the AOS we also have sent one postdoc and one student to ALS to help build our system because we collaborate people from the ALS. Also, this machine or this instrument already shipped back to the TPS already. So finally, I like to acknowledge all the people, particularly the neutron measurement. We thanks Dr. Garner. Okay. Also, we run some of the risk measurement at NSRC. On DG. And the samples provided Professor Kimura from Osaka University. Okay, thank you.
Question or comment? So, from data you show that there's an anti-ferro, at low temperature there's a short-range anti-ferro correlation.
Mm-hmm.
But how is it related to the spin glass order? I'm not sure I understand. And also the second question is that the glassy order, normally you have some kind of hysteresis. The field pool, your field pool kind of.
You just mentioned the elastic here, yeah?
No, elastic. There's a shortage correlation.
Yeah. You mean this one?
Yeah.
Oh. Sorry. I cannot catch you mean. You mean
So I mean, you start to have this correlation build up at lower temperature, right?
Yeah.
But how does it relate to the glassy order? That because normally we see that in glass you don't really have a kind of making order, right?
Yeah. So that's almost we're still working on this system, but we try to understand whether this correlate your correlation length or not. If you have large correlation length, usually you can keep the anti-ferromagnetic become the more possibility higher, right? If you don't have the correlation length, then you probably just randoms or frustrates, no any correlation. Okay, so if you the AB plane you have larger the correlation implied you may have the either the ferro or anti-ferro that kind of spin interaction relate to this kind of interaction. Okay, so if you look at this our parents compound, all of them are anti-ferro. So if you have larger the correlation length, which means you may have the more higher probability to form the anti-ferro that kind of interaction. Okay, that's we propose use correlation length to explain the XY plane like this tornado structure rather to 3-dimension iceberg. Okay, but our more historic measurement we will carry out end of this month. We want to use small angle. Then you probably can see the more direct this kind of future. I mean that we can carry out the small angle neutron scattering. You can map in the spin on the plane or CX to see that's one. Okay, so we right now provide the correlation length, doesn't directly provide the evidence, honestly. Just give some kind of idea. If you have larger correlation length or correlation function, then probably can imply that you may have more strong XY like spin glass system rather to the CX.
I tried to catch the picture of structural correlation with the speed. So, because here you show honeycomb type, you have a different structure with the orthorhombic, right? Because from the regular X-ray, you show the structure is orthorhombic. But now your speed structure is not orthorhombic, it's a kind of honeycomb type. Are they kind of correlated? Okay, this. So, okay, so they are really correlated.
We try to map it, okay? Small angle can map it. Finally, the AB plane or CX, the structure will have the like a SkyMe, that kind of structure or not. But that's we needed to carry out. But if you look at this, CX sim doesn't large is the correlation length based from our neutron scatter measurement. But the AB plane sim much large is correlation length. That means within this range, you can see the interaction between the magnetic ion. That's we try to propose.
So the interaction more than 1 unit is extend like a
That's
zero
right.
unit
That's right. That's if you no correlation, that means you have no any interaction with each other. So that's we try to propose this.
Any other questions? I got a simple one. So based on what kind of experiment did Professor Kimura then propose this kind of XY plane order?
Oh, they just they have some kind of measurement, but if you look at this paper, probably can give you some kind of idea. Okay, they just propose. Okay, here propose. They think only see the tornado on the plane. Doesn't see. That's the reason we got the sample try to support his idea. Okay.
Okay.
So they so far they didn't solid evidence to see the really this XY 2 dimensions spin glass.
Yeah. Because if you want to have this kind of order, for sure you need to have a lot of competition in plane. I mean.
That's right. So we try to solve the correlation length, also distance between two magnetic ions. So we also use the correlation function rather correlation length. Okay. So they involve two wireless correlation lengths, also the two magnetic ion distance. If you go close, your interaction becomes the most stronger.
Right. From your experimental data, what's really surprising to me is that nickel and manganese they are both 2+, which means that the orbital degree of freedom has already been quenched. So there should be no chance for orbital ordering. But you did see nickel orbital ordering.
No, that's preferring.
Okay.
Preferring. I just mentioned, but from so X-ray scattering, I needed to mention here. Okay, this not the orbital ordering. This.
Yeah, from the linear dipole experience.
That's right. Let's give you the orbital preferring.
I see.
Not the ordering.
I see. So in this sense, which means that there is some kind of charge disproportionation at low temperature to make this happen. Otherwise, there is no orbital degree of freedom.
That could be, but I'm not sure. Okay, like here, this just give you the orbital preferring. You have measures major probability like low temperature you have S squared minus Y squared.
Okay.
So if you want to probe the auto ordering, you have to run the X-ray saw X-ray. That's right. If you have very nice ordering, you will have a very strong diffraction peak come out to the low temperature.
Okay, so far
However, we try to solve this